Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Hello students. So we are learning chapter 2, that is schema design. So in the previous session we learned about how to identify the functional dependency, and we also learned how to identify whether functional dependency is trivial or non-trivial. So we will discuss some of the examples based on how to prove whether it is a trivial or non-trivial. So I just told you in the previous lecture a shortcut about the trivial such that if RHS is a part of LHS, then it is a trivial, otherwise non-trivial FD. So once again I will write that definition. That is, functional dependency are categorized into two varieties. One is a trivial FDs and the other one non-trivial FDs. Okay. So what is a trivial FD? We understand trivial FD is nothing but if RHS is a part of LHS, then we can designate it is a trivial FD. So trivial FD is nothing but if beta is subset or equivalent to alpha, then alpha gives beta trivially. So that is a shortcut I told you, that if RHS is part of LHS, then it is trivial FD. And now we will see a definition about non-trivial FD. So what is a non-trivial FD? Non-trivial FD means, I will tell you like this: if RHS is not part of LHS, then it is non-trivial FD. The shortcut. So I am writing one equation, that is, if alpha intersection beta is equal to pi. Right, understand once again. If alpha intersection beta is equal to pi, then alpha tends to beta is non-trivial FD. Simple definition. These are all shortcuts. If alpha tends to beta is not equal to pi, then alpha tends to beta is which FD? Trivial FD. That's it. Okay. So once copy them, we'll look at few examples, and in this lecture we also solve your classroom workbook problems, which consist of gate questions also. Copy it. Okay guys, I hope so you have got copied. Now let us work out some examples based on the equations. I am saying there is a table R which is having AB, so 10B1 and 20B2 and 30B3, and I am listing out some dependencies A to A, AB to A, ABC to A to B, B to C, AB to D. Identify how many are trivial and how many are non-trivial functional dependencies. So is asking question, find number of trivial FDs, comma, number of non-trivial FDs. So the solution. You say A tends to A. What I said? If RHS is a part of LHS, it is trivial or non-trivial? It's very simple. It's what? If RHS is not part of LHS, then it is a non-trivial. Otherwise, it's a trivial. Otherwise, you look at into this. If alpha intersection beta is not equal to pi, then alpha tends to beta is trivial. So come to the first, A tends to A. Now you tell me, A intersection A is not equal to pi. Yes or no? Because what is the common? A which is not equal to pi, hence I can write this is which dependency? Trivial dependency. Otherwise, RHS is a part of LHS, hence it also comes under into trivial. So come to the next. AB tends to A. Once again, AB intersection A is not equal to pi, so hence it fall into trivial FDs. Why? RHS is a part of what? LHS, very simple. So likewise, if you observe the given dependencies, how many are trivial and how many are non-trivial? So already we understand 2 comes under into trivial, and next one we point out this is also what? Trivial. Why? RH is a part of LHS, and next one is need to carefully observe. So what I said, RH is not part of LHS, and one more condition I said. What is the one more condition? A intersection B is equal to what? Pi. See the condition. If alpha intersection beta is equal to pi, when there is no common between them, I can write this is in which category? Non-trivial category. And the next one, B tends to C. This also comes under into non-trivial because beta is not part of LHS. And next one, AB tends to D. It also comes under into non-trivial. Why? Because the RHS is not part of LHS. So this is how I can write how many are trivial and how many are non-trivial. So how many are trivial? Find a number of trivial FDs. Trivial and trivial and trivial and non-trivial are 3. So 3 comes under into non-trivial and 3 comes under into non-trivial. I hope so you got understood. Very simple. Copy this example. Okay, students. So these are all the tricks you have to learn. So as much as possible, we are going to provide some kind of shortcuts. Shortcut plays very important role in GATE examination public sector undertakings, where you can able to minimize your time. So that by seeing the bit, you could easily answer within less than 1 minute of time. Right? So let us concentrate some tricks which are mainly teach in classroom. So I hope so you are clear about this example. So we have learned from functional dependencies by giving some data how to identify whether it is functionally dependent or not functionally dependent. And we also identify from the second part that how many are trivial FDs and how many are non-trivial functional dependencies. Okay. So before we discuss about classroom work problems, let me give one more example like this. There is a table R which is having A and B and 10B1, 20B2 and 30B3 and 10B2. So I am asking how many non-trivial FDs are satisfied. So you know what is the meaning of non-trivial FDs? Non-trivial FDs are nothing but the RHS must not be the part of what? LHS. Yes. So tell me how many you can derive from the given R. I can write A2B1 and I can write B2A1. I can write A2A1. I can write B2B1 and AB2A and AB2B and that's it. These are the maximum possible functional dependencies. In this, he is asking very clearly what? How many non-trivial functional dependencies. So in this, what are trivial and what are non-trivial? So this comes under into trivial, this comes under into trivial, this comes under into trivial and 2 also trivial. So our concentration is about these two combinations. Now for a given data, you identify how many are satisfied against to the given data. Okay. Now tell me A to B is satisfied, A tends to B is satisfied, 10B1 satisfied, 20B2 satisfied, 30B3 satisfied, 10 is repeating. When 10 is repeating, what has to repeat? B1 has to come, but what is given? B2. And this indicates that A not implies B. So overall, it's what? A not implies B only. And so let us prove B tends to A. So what is the B tends to A? I say B1 10, B2 20, B3 30, B2 10. Now you tell me, first one is satisfied, second one is satisfied, third one is also satisfied because B3 is unique. But fourth one you observe carefully, the B2 is repeated. What has to come against B2? 20. So it's wrong. And so overall B2A is failed here. So therefore B tends to A is also failed. So finally, how many non-trivial FDs are satisfied? The answer is how much? 0. You got to understand? Now copy this. Okay guys, now we understand how to solve these kind of questions if at all examiner asks you. Now let us see another small example. R A B 10B1 20B2. How many trivial FDs are satisfied? Okay, you know what is the meaning of trivial. Very easy to identify why RHS is a part of LHS, then it is a trivial, sublime. So can you write possible trivial FDs? So can you guess? First combination A to A, second combination B to B, third combination AB to A, fourth combination is AB to B. Anything else? You may guess one more. AB to AB. AB to AB is nothing but AB to A and AB to B. Now you tell me how many are satisfied as per as the given data. Let us check. A to A. Take A and A data. 10, 20. Right side what to write? Yeah, right side same 10 and 20. Satisfied or not? It is satisfied because 10 is unique, 20 is unique. We don't mind about the dependent. What is the next one? B to B. B to B also. B1, B1. B2, B2. This is all satisfied. And what is the next one? AB to A. So write AB data and A data. AB data 10B1, 20B2, 10 and 20 satisfied and satisfied, ultimately satisfied. And what is the next one? AB2B, and you write A data and B data and B data 10B1, 20B2, B1 and B2 is also satisfied. So all will be satisfied. Why? As I told you, I note in the session that, what is the note? Trivial FD is by default satisfied. You need not check as like this. So blindly you can say all possible trivial functional dependencies are by default satisfied. There is a waste of time by doing like this. All will be satisfied. So what is the answer as far as this concerned? All trivial FDs are being satisfied. I can write 1, 2, 3, 4. Why? Because it's nothing but AB to A, it's nothing but AB to B. I have written them. So answer is how many? 4. Okay, got it? So don't do any kind of extra work for the trivial FDs concerned because trivial FDs by default satisfied. Our concentration only for non-trivial functional dependency, whether to be satisfied onto the given data or not. Note. Okay guys, now we do classwork problems. Whatever we learned so far regarding functional dependencies, trivial or non-trivial, or how to prove functional dependency when a given data is available. So the idea behind proving functional dependency is nothing but as long as alpha is unique, I can say that it is proved. If alpha is redundant, then you have to see that beta is redundant or not. If beta is also redundant, I can come to know that it is proved, otherwise it's not proved. And in proving, there are two kinds of dependencies you can say. One is a trivial FD, the other one non-trivial FD. So trivial FD is very easy to prove and nothing to prove because they are already existed in the schema itself. The idea behind trivial FD is nothing but if RHS is a part of LHS, then it is a trivial. And if at all it is not a part, then you need to see that it is a what? Non-trivial functional dependency. So you need to prove non-trivial functional dependency against given data. Okay. Now you open your classroom workbook. Your classroom workbook, question number 1. Classroom workbook of chapter 2. Question number 1. So what is the question number 1? So look at. He has given question number 1 a schema of R ABC with some tuple set and asking how many non-trivial FDs are satisfied. You know how to do this. So let me do here. So R is given with ABC and some data is present over here. A1, B1, C1, A1, B1, C2, A1, B2, C2 and A2, B1, C3. So this is the information we got. Now he is asking find a number of non-trivial FDs. You know what is the meaning of non-trivial? What is the meaning of non-trivial? You need to derive a production such that RHS is not part of what? LHS. Now you tell me, what are the possible dependencies? Possible non-trivial FDs. Tell me. A to B I can write and B to A I can write, B to C I can write, C to B I can write, and what else? A to C I can write, C to A I can write. Anything can I write? Yes. I can write AB to C and I can write AC to B and I can write BC to A. That's it. So these are all the possible occurred non-trivial functional dependencies on the given relation R. Now you check whether these are all the specified functional dependencies non-trivial one are satisfied with the given data or not. So what is the given data? Once again you check. First tuple is A1, B1, C1. Second tuple A1, B1, C2. Third tuple A1, B2, C2. Fourth tuple A2, B1, C3. Okay. Now tell me, A to B is satisfied or not? Let us check. Here in A to B, A is a determinant, B is a dependent. So A is a dependent determinant, B is a dependent. So satisfied. Now you check the second one. So whenever A1 is repeated, what has to repeat it? B value has to repeat. So B value is repeated. So again the third tuple is also A1. A1 is repeated. What has to repeat it? B1 has to repeat it. But is B1 repeated in the third time? No. And A to B is not satisfied. And the second one, B to A. What is a B to A? B is a determinant and A is what? Dependent. So B1, what is the value? B1 is a unique, so no problem. B1 is unique or redundant? Redundant. So when B1 is redundant, what has to come? A1 has to come, so it is repeated. Then come to the next one, B2 is unique, yes, unique. Whenever alpha is unique, you don't mind about beta value. B1 is unique, no, B1 is redundant. When B1 is redundant, what has to come? A1 come. Is A1 arrived? No, it is given what? A2. And this is also wrong. What is the third one? B2C. Now what is the B value? B1. It's fine. B1. It's a unique or redundant? Unique or redundant? Redundant. So when it is redundant, what has to come? C1 has to come. But what is given? C2 has given. And it is also what? Wrong. And what is the fourth one? C2B. This time C is a determinant, B is a dependent. C1 fine, C2 is unique fine, C2 is redundant. Whenever C2 is redundant, what has to redundant? B value has to redundant, but B value has given how much? B2, but actually it was what? B1. And whenever alpha is repeated and beta is not repeated, and this is also what? Failure case. And the next one, A tends to C. A is a determinant, C is a dependent. A1, it's a unique find, A1 is a duplicate, against A1, what has to come? C1, but what is given? C2. Hence, since beta is not repeated, it is also wrong. And what is the next one? C2A. So what is C2A? C1, against value is what? A1. What is the next one? C2 is a unique. What is the value? A1. Next one C2. Whenever C2 is coming, what has to come? It's A1 value. So A1 is also repeated. And C3 is a unique value or old value? Unique value because C3 is not appeared earlier. Hence, this is the proved one. And next one, AB to C. This time, AB is a determinant, C is a dependent. So A1, B1, C1. This is fine. A1, B1. Since A1, B1 is repeated, what has to repeat? C1 has to repeat. But what is given? C2. So hence, this is also what? Wrong. So what is the next one? AC tends to B. AC is now determinant. A1, B1, A1, C1. What is the value? B1 value. A1, C2 is a new value. A1, C2 is redundant value. What has to come? B1. But what is given? B2 is given. And this is also wrong. And next one, ninth. What is that? BC tends to A. What is BC? BC is a determinant. B1, C1. A1 is the value. B1, C2. Is it unique or redundant? This is unique or redundant? This is unique because earlier B1, C1. Now this is what? B1, C2. So B1, C2 we don't mind the dependent value. B2, C2. Is it redundant or unique? Is also unique. B1, C3 is also what? Unique. Since all the combinations are unique here, and so I can say automatically it is proved. So find the number of non-trivial FDs which are proved. So the answer is what? 2. Only 2 non-trivial functional dependencies are being satisfied against given data. Okay? Copy. So this is the first question of classroom workbook based on functional dependency. Yeah. Okay, students. I hope so. You understood and got copied. So now we will solve question number 2 of classroom workbook based on functional dependency. Question number 2 of classroom workbook based on functional dependency. It's also very similar to question number 1, so we could solve very easily. So what he said, he has given question number 2 of classroom workbook of functional dependency topic. He has given table R with 3 attributes ABC, and the tuples are 1 2 3, 4 2 3, 5 3 3, and he is asking which is does not hold. Does not hold means which is the dissatisfied one. So as usually, let us check the solution over there. So what is the solution? Let us check first of all A tends to B. So what is A value? 1. Unique value, no? We don't mind about the dependent whenever alpha is unique. Please look at the flow chart. And what is next one? 4. Unique or redundant? It's unique. What is the 5? Unique or redundant? It's unique. So it's satisfied. Whenever alpha is satisfied, automatically beta is satisfied. So option B. BC tends to A. This time your determinant is BC, dependent is what? A. So 2, 3, 1. Yeah. Oh, this is a too dangerous. 2, 3. What is the value is given? 1. Again 2, 3 is repeated. Whenever 2, 3 is repeated, what has to come? 1. But what is given? 4. Hence this is the wrong one. You get my point? So 2, 3 has come first of all, and its A value is 1. Whenever 2, 3 is repeated, 1 has to repeat, but it is given as 4, and so is wrong. Option C, B tends to C. So 2, the C value is 3, again 2 is coming, C value is also repeated, fine. 3 is a unique value, no problem, this is success. Option D, AC tends to B. So what is AC? 1, 3, unique value, 4, 3, unique value, 5, 3 is also unique value. So whenever alpha is unique, we don't mind, it is satisfied. So the answer which is not satisfied is B. Right? So now we solve question number 3 of functional dependency of classroom workbook. So this was given in GATE 2002. Again I am repeating question number 3 of classroom workbook, and which is given in GATE 2002. So what he asked here is a very similar question to that. R is given as XYZ and some tuples are being present. So he is asking which is satisfied. That's it. Now how to solve this problem? In a simple manner. Option A, xy to z. So xy is the determinant, 1 4, no problem, unique value, 1 5. Unique or redundant? Unique value. Don't look at A, you have to look at xy together. Don't alone look at x and don't alone look at y. You have to take the combination because xy is what? Determinant for us. So 1 4 and 2 is given, 1 5 is unique, 1 6 is unique, 3 2 also unique. Hence this is satisfied. You have also how to check z to y. Z is a determinant, y is a dependent. Z is a determinant, y is a dependent. So 2 is a unique value, 3 is unique value, 3 is a redundant value. You have to be very careful here. So whenever 3 is repeated, what has to repeat? It's 5 has to repeat, but what is given here? 6 is given here. Hence it is wrong. So overall it is wrong. Okay now. Now come to yz to x and y to z. So 4 2, it's unique. 5 3, it's unique. 6 3, it's unique. 2 2, it's unique. So this is success. Y to z. 4 2, 5 is unique. 6 is unique. 2 is unique. So it is also satisfied. Hence it is correct. So what is the answer in that? Option B is correct because other options will be wrong automatically. Okay. As you want to check, you can check. So yz to x. 4 2 is unique. 5 3 is unique. 6 3 is unique. 2 2 is unique. So this is correct. But what about x to z? 1 is given with 2. Yeah, 1 is repeated. What has to repeat? 2 has to repeat. And this is wrong. So overall this is wrong. Z to x, z to y. So 1 2 4 1 3 5 1 3. Yeah, here is important. So whenever 1 3 is coming, what have to come? 5 has to come. But what is given? 6. Hence this is wrong. So overall it is wrong. So the only one option is what? Option B. Okay. You copy. We will do question number 4 of classroom workbook of functional dependency. I hope so. You understand question number 2 and very similar question which is asked in GATE 2002. This is a 2 marks question. See how easy it is to prove it. Yeah, okay guys, I hope so. You understood question number 2 and completed yourself, and you understood question number 3 and completed yourself. Now let us do question number 4 of classroom workbook. It is also one of the previous GATE question. Question number 4 of classroom workbook, which is also asked in GATE 2002. This is also 2 marks question. So he said he has given same R of ABC with some tuples 111, 110, 232 and 232. is asking, we conclude that A to B and B to C Now you can guess which option is correct as far as given 4 options. Let us take first one, A to B and B to C. Okay. So A to B, A is a determinant 1 against B value 1. And here this is a 1. So when 1 is repeated of A, what has to repeat? B value also repeat. It's correct. B value is repeated. 2, 3. 2 is a unique. So 3 is against value for 2. Again 2 is repeated. What has to repeat? 3 has to repeat. So it is repeated. Fine. Come back to another. B to C. This one I am checking now. 1. What is the value of C? 1. When B value is repeated, what has to repeat? C value, but what is given? 0. And this is wrong, and it is wrong. So option B, actually A tends to B is true. So that's why it is also not concluded. And come to B not implies C. So 1 and 1, 1. What has to come? 1 has to come. So hence it is B not implies C is true. It is a false. It's a false. It is true. Now since option D you check carefully, A not implies B is a false. This is a false. And this is a true. Ultimately it is a what? False. So what is the correct answer? Option C is the correct answer. Okay. So that's how you could do questions using functional dependency rules. And you also know how to do trivial and how to do non-trivial functional dependencies. Okay. So the logic behind all these functional dependencies is inference rules. These are also called as Armstrong axioms. Okay. Whatever we proved, whether a functional dependency is satisfied or dissatisfied, it all depends upon Armstrong axiom. There are few varieties, sound and complete. This is known as sound rules. This is known as complete rules. So sound rules are 3. One is reflexivity. Number 2, transitivity. Number 3, augmentation. 3 properties comes under into sound. And what are the complete rules? Union rule, union decomposition, accumulation, pseudo-transitivity. Can copy them? So whatever examples we have proved so far, those examples I have proved based on these rules only. So that's why these properties are known as functional dependencies. Inference rules are also known as Armstrong axioms, which fall into 2 categories, sound rules and complete rules. Sound rules. Number 1, reflection. Number 2, transitivity. Number 3, augmentation. And complete rules. Number 1, union rule. Number 2, union decomposition rule. Number 3, accumulation rule. Number 4, pseudo transitivity. Okay guys, I hope so. You have completed the left hand side question number 4 and right hand side functional dependency inference rules and Armstrong axioms. We will discuss these Armstrong axioms in the next session along with attribute closure and key derivation. So thank you very much for watching us.